Sprinting down the mountain, trying to chase after it. Brand new deck too, got run already.
We're warming up. Okay, so let's continue with chapter 16. We did confirm in the book that it is chapter 16, so I was right. My notes were wrong. I don't know why I was thinking it was 18. So we're chapter 16, roofing. So we're going to start. We talked earlier a lot about what we would consider to be the regular sloped roofs. Okay, so I'm going to spend more time on this roofing talking about low slope roofs, or what are typically called flat roofs, which aren't really flat. So the thing about a low slope roof is that it has a rise over run that's less than 2 and 12, right? So 2 inches and 12 inches, or 2 feet and 12 feet. Okay, so it's about 17%. So terms to kind of get used to when we're talking about low slope roofs. The roof deck is the structural surface that supports the roof. So we've already covered this in pretty big depth, okay, along the way. So that shouldn't be too hard. We have some form of thermal insulation, right, that's installed to slow the penetration of heat or cool. And then we have some kind of an air barrier that basically restricts the leakage of air through the roof assembly, right? There's going to be a vapor retarder, okay, which is something that it used to be called vapor barrier, but the truth is nothing is perfect, so they changed it to be vapor retarder. And it's going to not allow, it's going to control where the condensation would occur in a roof assembly, and we'll explain what all that means in a second. And then we have the roof membrane itself, which is the impervious sheet that doesn't allow water to penetrate. So we've got all these different terms that we're going to be working through. We also have drainage, right? Some way for the water that's on the roof to get off the roof. And then we have flashings, which just are joining pieces of roofing together. They're going to prevent water from infiltrating at the joints, right, or at edges, which we'll get into more depth in a little bit. Okay, so let's start with roof decks. Roof decks are composed of the typical methods that we've seen before. Okay, so think back to the concrete, right, lecture, where we have the concrete slabs precast, right? As an example, they can be cast in place. Those can serve as roof decks, so we can put the roofing on top of that. We can have a wood frame house that has a flat roof. Okay, so we can have the same kind of thing where we have roof sheathing. And that just goes on top. All right, the roofing and everything goes on top of that. So the deck needs to be stiff under whatever the expected loading is on the roof. Sometimes it's just the roofing itself. Sometimes it's more. Sometimes it's air conditioners or what have you. And the deck must resist the wind uplift, right, or any kind of seismic loading. No surprise. The decks must also slope sufficiently toward all drainage points to make sure that the water gets from one point to where it needs to go. Okay? There can be trouble that occurs if it doesn't do that, and we'll talk about that in just a second. The minimum slope for a flat roof is 1/4 inch per 12 inches. So it's 1 to 50, okay, which is not very much. So it can be almost flat, but it has to have some slope. This is a really good example, photograph here, of adding just a little bit of slope. So you can see that these little sleepers underneath here. So we've got our main deck underneath. Then we have these little sleepers, and then the plywood's being installed on top of those sleepers so that it slopes a little bit, right, to wherever our drains are, in this case, the edge. So that's always going to happen, okay? So there's a couple different ways that we can vary the height of the roof or to get that slope. We can vary the walls and therefore the joists that span whatever that roof deck is. We can also have a flat deck, right? And then we can put tapering insulation in, or those tapering little sleepers that I saw in the last slide to give us the slope that we need. Okay, so it's going to vary based on what the particular installation is. If, for example, you had a concrete slab, typically that's going to be flat and you're going to use some other form to get your taper. If you had a wood frame building, maybe it's easier to just raise one set of the walls such that it slopes a little bit. It's going to vary a little bit. If we don't have that slope, you're going to have what's called ponding. Okay, and this is very, very common, and there's a great example. I used to take the class when this was a separate lecture and I wasn't trying to cram it all in. We used to go walk over kind of outside where the lecture hall is. I think it's 112, right? There's a whole bunch of air conditioning that's been put on top of that. So sometime when you're on campus, go over there and look at it, okay? That air conditioning equipment is too heavy for that section of the roof, and it's caused the roof to pond. When the rain happens and it ponds, right, it slowly deteriorates that particular area because it keeps a pool in that area, deteriorates the roof. So if you look up there, you see that's where it all drains through. Okay? So that ponding has an effect that will eventually deteriorate whatever the roof membrane is itself, which cause leaks and ultimately failure of the roof. Okay? The other problem with ponding is that it can get progressively worse. So what happens here is it starts to pond. Okay, we add the weight of the water, right? And water's really heavy. Have you ever tried to carry like a 5-gallon jug of water? It's really heavy. Okay, so you add that water in, it causes the roof to sag. Then more rain happens, right? It causes it to sag further. Gets heavier, even more sag, right? So ultimately you get really big puddles, right, or ponding, just because the roof just gets progressively worse. So you can end up really running into trouble. Okay. So when we get to roof decks, the roof membrane itself needs to be laid over a smooth surface that doesn't have any gaps, knot holes, or protruding fasteners, right? We don't want any screws coming up from below because it'll destroy the membrane itself. All right? Likewise, we need whatever the roof surface is to be nice and flat and to slope in the direction that we want it to slope. The other thing is that decks need to be dry before we apply the roofing material. So if you're building your building and it rains, you can't just run up there and put the roof on, right, if it's wet. So you need to let that dry out before you actually put the roof assembly in place. Okay? So the vapor retarder is kind of the next big thing that we have to talk about. And this is not something that's as common around here, but it's something for you to be aware of. Okay? So when we put the thermal insulation, it's going to, in this instance, it's going to be below the structural deck, or between the structural deck and the membrane, or above the membrane. So we've got 3 different conditions, and I'll walk through each of those conditions in just a second. So if we put the insulation below the deck, okay, so this is your typical wood frame house, right, where we have our joists and we're putting our insulation in between, then we cover our joists with sheathing, and then we're putting our roofing membrane and stuff on top of the sheathing, okay. When this happens, okay, they're the typical fiberglass bats. There needs to be this airspace that we talked about. Right, even if it's a flat roof, even if it's not pitched, so we get that air circulation. And I think it's on the next slide. Okay. In cold climates, you're going to put what's called this vapor retarder against the warm side of the building. Okay. And so we don't worry about this that much in California, and this applies for roofs, but it also applies for walls. And the idea of a vapor barrier is, let's say we're up in Alaska, right, and it's really cold. Okay. If we heat the inside of our house, right, and the outside is really cold, at some point in the wall we're going to get condensation. And so if we put our vapor retarder, our vapor barrier, right, on the outside of the insulation, for example, the condensation point would occur between that vapor retarder and the insulation, and all that moisture would happen and give us mold inside our wall. So instead, we put that vapor barrier, that vapor retarder, right, on the warm side of whatever our insulation is, right? So that barrier is always going to go there. So if the condensation happens, it happens on the inside, right, on the warm side. So it's not going to get into our wall. It's not going to destroy our wall cavity. It's not going to give us mold and mildew inside our wall. Let's say we're in Hawaii. Okay, completely different climate. It's really hot. Okay, we're going to put our vapor barrier in, but typically the opposite is true. We don't heat our house in Hawaii, right? We have the air conditioner running in Hawaii. So if that's the case, right, the cold side is the inside and the hot side is the outside. So if we were putting our vapor barrier, our vapor retarder in place, right, it would go on the outside of the insulation, right? Because the condensation would occur on the outside. So you have to vary it by climate. So the big question comes with, we're now in California. Where do you put the vapor barrier? Right? You could argue that it could go on either way, right? Depending on what season it is. So this is why, typically in California, we don't put them in, right? So we use in California, and more this is becoming common, we use what's called Tyvek, okay? And that's the brand name for this. It's a very specialized paper, so to speak. It's kind of a plasticky paper. And the way the weave of Tyvek works is that it allows moisture to pass through it in one direction but not in the other. Okay? So we wrap our buildings in Tyvek, right, such that any moisture that occurs on the inside of the building is allowed to pass through to the outside, but that water that's on the outside can't get through the barrier to the inside of the building. So in California, we do that because we can't really place where that vapor barrier belongs, because we have consistent, our seasons vary too much. If you were in Tahoe, maybe you could place it on the inside, right? But it depends, again, on exactly what the climate conditions are, and that's the important thing to realize. So the same thing happens if we're talking about roofs, right? In terms of where we place that vapor barrier, okay? So we can also use spray foam, no surprise, okay? So in this instance, we're talking about insulation between the deck and the membrane. So this is where we don't want our insulation in between our joists. I apologize, it's a little dark right now. We don't want our insulation in here, right? In this case, we have our deck. We're applying our rigid insulation outside of our deck, right? And then we're applying our roof membrane on top. So this is usually some kind of, styrofoam insulation, or it's some kind of lightweight concrete, okay? The nice thing is that the insulation is going to protect the deck from temperature extremes, so we're not going to get really wild things happening. It's also protected from the weather because you've got a membrane over the top of it. Okay? If you're in cold climates and you use this method, okay, you need to make sure, right, that you actually vent this, because you can have troubles. Okay? So this is, again, we have our deck or our lightweight concrete here. Okay? When we put our vapor retarder, right, it's going to be installed below the insulation, right, against the membrane, okay? But we can have condensation that occurs, and so we need a way to get that out. So we have to install these special vents, right, that depending on the condition, whether it's hotter or colder, will allow the moisture in but not out, okay? It's kind of a specialized case. I'm not that worried that you understand it. Just be aware that this requires some special venting, okay? Now the last way we can insulate a roof is that we can insulate above the roof membrane itself. Remember, the membrane is the part that prevents water from penetrating the building, okay? So in this instance, the membrane is going to be protected from the temperature extremes. So remember, anything on a roof is subject to really hot sun, right? And also weather conditions, so it can deteriorate faster. So if we put the insulation above that, right, the insulation is subject to all those weather conditions and stuff, but the membrane isn't, which is nice, okay? And the other thing is that the membrane is typically on the warm side, so it's already acting as the vapor retarder, or the vapor barrier, so we don't have to worry about putting one in. So it can be advantageous in that sense. Okay? So what happens, though, is you need some kind of a special membrane because, right, the material that's insulating must retain its properties when it's wet. So we couldn't use fiberglass bats, for example, because as soon as they get wet, they lose the insulation value, right? So it needs to be a special type of insulation. And the membrane can't decay or disintegrate when it's exposed to sun, water, snow, right, rain, all that stuff. So it needs to be kind of a specialized case. The material also should have a high thermal resistance, right, because that's your insulation, keeping the sun out. It needs adequate resistance to compression, right, or decay, so if you're walking on it, you're not going to destroy it. And it needs to also have a high resistance to melting depending on what the membrane is that you're actually using, because a lot of times the membranes have to be hot, right, in order for them to fuse together. Okay, so when we talk about a vapor retarder, right, we're talking usually about 2 layers of asphalt saturated felt, right, that have been basically glued together, right, and they overlap. One runs in one direction, one runs in the other direction, okay? And they're going to be adhered to the roof deck itself with some kind of a hot asphalt, Okay, asphalt's just a petroleum-derived or a derivative of petroleum. You distill petroleum to get asphalt. The other thing is you can use what people referred to earlier as bitumen, which is that bituminous kind of a rubberized tar-like membrane. There's an example of it in the back that I can go grab a little bit later on. So the vapor, we've already talked about this, but the vapor retarder must be located within the assembly on the warm side of the insulation. Okay, so you have to be aware of that. It can be plastic like this, except on a corrugated deck, etc. Okay, so let's talk about the roof membranes themselves. Okay, so there's 3 different types of membranes that you can use. One is a bituminous roof membrane, right, which is again kind of a rubberized plastic. I should really, you guys bear with me for a second while I hobble over here. I'll look around for it afterwards. Okay. Then we can have single ply roof membrane and fluid applied roof membrane. So I have some examples that I'll pass around when we get there. Okay. So if it's going to be a bituminous, there's a couple different types. You can have a built-up roof membrane, okay, which is assembled in place from multiple layers of asphalt felt. The felt is delivered to the site in rolls. Let's see if we can, the best example. Okay, here's the asphalt felt that we're talking about. These are obviously small squares of it. They come in rolls, okay? And the joining, what I mean by the bitumen, the joining piece, right, is going to be the asphalt, right? So it's going to be kind of a liquid tarry substance that's going to join them together. So you're going to lay these such that one set of rolls is going this way, the next set of rolls is going the opposite way, and that assembly is then giving you the waterproof membrane. So this is the felt. Yeah.
Is that when they're sitting up there with a torch?
Yes and no. It depends on the exact method. Okay, you can do something like this where you're applying the hot tar to the rolls themselves and laying them out. Sometimes it's going to be slightly different where the material itself has that the asphalt layer on the sides, and you'll flame it to heat it up, and then when it laps, it'll actually seal. Okay, which can be, jump back one second, one of these single ply roof membranes. So it can be one or the other. It's going to vary slightly. Okay? So it needs to be applied hot in order to merge the saturants in the fibers. So that felt has this asphalt already in it. And so when you heat it up, it starts to melt together, which is part of the advantage of it. It ends up forming a multi-ply membrane. The felt is going to be applied in overlapping layers, and it's going to be 2 to 4 plies thick. Okay, so you're going to end up with something a little bit thicker. Now this may have a few other pieces. Let's see if we can count. Now this looks like about 4 ply. Okay, we'll talk about the top surface of that in just a second. Okay, once they're all put together. Okay, so here we are. This doesn't have the fancy little machine that's applying it. Okay, we've got our bucket of our asphalt tar, and we're spreading that and then rolling this roll across that particular piece of roof. Okay? So finally, you're going to put a layer of crushed stone or other kind of a granule on top. Sometimes the last layer is going to be like this one, right, where it has the granules already built into it. Okay? And that's going to protect your layers from the sun, right, and from people walking on it, which is the other big problem. Okay, so it's going to protect it from damage. Sometimes it can be a layer of rocks more like that, right, where you have a nice layer of tar and you put the rocks in it, as opposed to something like that roll. So here's our example. Okay, we have our concrete deck, and we've got our asphalt primer coat that we're painting down. Then we've got all our layers of felt that are overlapping, right, that have those members in between. Then we're putting our rigid insulation board on top, and then we're putting our aggregate on top of that. Okay, so again, this is the membrane is protected by the insulation in this particular example. So it's going to vary a little bit. Okay, So now we can also have this bituminous roof membrane, okay? This is the one that I can't find an example of. This is a specially engineered material. It can be self-stick, sometimes it can be flame stick, where you've got these various pieces, so instead of using the felt, it's actually more of a rubberized piece that sticks to itself, okay? And so you can use that. I'll have to dig around and see if I can find one. I know there's an example here somewhere, okay? So it's been kind of engineered for this purpose, which is the important thing to understand. So it's better than those layers of felt that are overlapping, okay? So it comes again to the site in rolls. It's going to be applied in overlapping layers the same way. They can be torch applied, hot mopped, cold applied, self-adhesive, right? So we've got a variety of different methods depending on the material itself in terms of, will it adhere by itself? Does it require some form of a torch? So if you've ever seen somebody doing roofing where they actually walk along with a torch and heat up the various pieces, this is what we're talking about. And then again, the topmost layer needs to be that piece that has the granules already built into it, right, for protection, UV protection, etc. So here's our example. We've got our corrugated steel deck, then we've got our rigid insulation here that are being fastened down. In this instance, they're floating a second set of rigid insulation boards on top of the first with asphalt in between, right? So the first set is actually nailed and fastened to the deck itself. The second set is basically glued in place, right? Then we're rolling our felt and our asphalt over the top, and then finally our aggregate, okay, which you've seen in what I passed around. So then we end up with what are called single-ply roof membranes. And so it's kind of like these, I believe these are actually both the single sheet membranes. So I'll wait and pass them around, but they're kind of similar, right? In this instance, right, we're only applying one layer to the overall roof. So it's the same concept, but instead of overlapping our pieces, right, we're just applying it once and that's it. So it tends to be a stronger material, right, in the first place. It requires a lot less labor because we're not overlapping our layers. We just put it down once. The problem is it's more elastic, so there's going to be fewer cracks and tears. You'll see these when I pass them around in a second. The problem is if there's one imperfection, right, water's going to get through. So you need to be aware of that. So it's going to be affixed by adhesives, or it's going to be affixed by a ballast system, so it's going to have rock on top of it to keep it down so it doesn't blow off. Thermoplastics, the sheets can be seamed by heat, and thermosetting sheets are seamed with kind of a liquid epoxy, so to speak. So actually this is, getting distracted here, this is what I'm talking about. These can be applied in a sheet that just covers the overall roof where you don't have any seams. They can also be seamed. So you can see that this is very different from the felt itself because it has little fibers in it, okay, that give it its extra strength. But this is not self-adhesive by itself, right? So you need something to stick it together. It's kind of more of a rubberized roofing material. Generally, if you're working with that kind of a material, it does require a special roofing contractor who's certified to work with whatever that particular material is. So you have to be aware of that. Okay, so again, if it's just a single layer though, and you have one accidental nail that pokes through it, right, you now have a leak. So there's no redundancy for something scratched the top surface, water gets through the top surface, but there's another layer underneath that blocks it. So that's the one thing that you're giving up, okay? And so the last type is a fluid applied roof, okay? Generally this is only used for a really complex shape. So if you can't do it with one of these other roofing, you can apply the fluid, and basically it's a liquid, and you apply it to the roof and it seals whatever you paint. Yeah?
Is that like you know, the thing that comes from the buckets, the Henry buckets?
Yeah, it's a lot like the Henry buckets. The Henry buckets are the do-it-yourself version of this. Not nearly as good as the professional ones, but the concept is the same. Something that you can actually pour on in a liquid form and cover whatever it is that you need to cover. And that's for really complex geometry. And sometimes you'll still use it in combination with one of these other methods. So in terms of ballasting and traffic decks, if you're going to walk on it or you need it to make sure it stays down, right, in a windstorm, you're going to put something on it that's going to weight it down like the rock, or you're going to put something on that gives you the ability to walk on it, okay? So this can be kind of the big challenge of roofs. We talk a lot in architectural design classes about, oh, this is going to be a roof deck, right? Well, if it's a roof deck, you have to think about how do you treat the roofing surface itself, because you've got that membrane that you can't have somebody walk out in high heels and punch a hole through, right? You need to be careful of that sort of thing, so you need something that somebody can walk on that's independent of whatever the membrane is itself. So a lot of times it's going to be some kind of a special decking that goes on top of the roof membrane, right, that gives us that extra protection so that we don't cause damage to the deck. The water tends to fall through the deck, right? So in this case we've got these tiles. Water's going to fall through the cracks to the membrane itself and then get transported off the site. Okay? Sometimes there's little plastic blocks that go underneath these to hold them up off the ground, right, or off the roof membrane itself, right? So they're all designed so that we can actually walk on them without causing damage to the roof. In terms of edge details, okay, assuming you're not trying to flow water off a particular edge, right, and we're collecting the water somewhere inside the site itself, we have to think about how do we fold these variety of layers up such that flashing can come over them so that if water falls here, it's going to flow down over our layers and into the roof itself, right? Right, again, it's the same principles of all roofing. We need to make sure that that water flows through. This is another example here where we have an edge that runs all the way around up here, but this happens to be a scupper, what's called a scupper, which is a place for water to actually leave and exit the building, right? They've got a downspout that catches it on the outside here. Notice all the extra layers of asphalt that are applied to make sure that that particular joint is sealed. The only problem with that is you apply all these extra layers and you end up with a little place for ponding to occur, right? Which can perpetuate the problem. So you always have to think through these when you're doing roofing. So it's very tempting to, we'll just put a couple extra layers of flashing in here. But every time you do that, you build it up such that water can't flow out as easily. Another kind of edge detail here, this is that drip edge that we've talked a lot about already today, making sure that water that flows will flow out and away from the building. This is kind of a proprietary system in terms of how it seals off the building. As you can see, this is a building separation joint, right? So we don't, if we have a separation joint between two buildings or inside of a big long building, right, for expansion and contraction, we need to seal that differently. Notice, as with any edge, we're going to carry the roofing membrane up, right, and then we're going to flash over it so that any water is going to fall down and to either side and not down inside the wall itself. So we're going to really carefully consider how we flash that. Just another example here. This is just an area divider. If we have one half of a roof that slopes one way, one half that slopes the other way, right, or we have too big of a roof to be able to do it in one continuous sheet, we're going to have this kind of a roof divider that's just going to make sure that the water flows away from our joint. Okay, this is a parapet detail. This is if the wall on the outside of your building extends above where the roof is, right? So this is the opposite of residential, tends to be for commercial buildings, right? Where we have this little parapet. Same concept here, where we need to make sure we pull the roofing up the side of the wall. Notice that there's always a 45 piece of wood that's in here, so that we don't have a tight joint, right? If I were to take, right, one of these asphalt sheets, I won't do it, right, and fold a nice tight joint in it, what would happen to it? It would crease and crack, right? And then I have a place where water can, right, seep in. I want to make sure that doesn't happen, so I use this nice little 45 to wrap it up the wall nice and evenly without any cracks, right? So that's always the strategy. Again, I have the sheet metal flashing that extends down over that roofing to make sure that any water that falls on the top of the parapet wall will flow to the outside. Okay? This is just a parapet wall being installed. This is like a demo of the wall cap flashing itself. There's no roofing here, or any kind of a membrane, which really bothers me, but you get the idea. Anyway, if we have an interior drain, right, we have to pay attention to making sure that the drain, right, that the notches in the drain are level with the roof itself so that we don't get ponding, right? And this is an interior drain such that the roof slopes to this at the interior, it goes into this pipe and gets carried away from your building, okay? So all of this has to be planned out in advance. Where do those flow through the building and where do they go to the outside, okay? This is a roof penetration for a plumbing stack, right? We talked about the need for those vent pipes for our plumbing. Same thing here happens, right? Only this time, again, we're building up with our 45s to wherever this cap is that's in sheet metal that goes over the roofing to make sure that if any water does fall here, it's going to flow out and down onto our roof. Okay? Structural metal roofing. This is just a set of metal roofing that's designed for the same purpose. I don't have a good example of it. That's why you get the default generic picture there. Okay, so let's talk a little bit about steep roofs. We're almost done. So in steep roofs, this is roofs with a pitch greater than 2 and 12. To me, that's not really a steep roof. Like a 4 and 12 roof doesn't seem particularly steep to me, but it's considered steep by the book's standards. So there's 3 typical categories. There's what's called the thatch roof, there's shingles, and then there's architectural sheet metal. Okay? So in terms of steep roof insulation, we already talked a bit about this. The vapor retarder is usually installed below the roof deck, right? So in this instance, it's going to be on the warm side of the building, so underneath this, unless we're in Hawaii, where it would be over it. Okay? If the underside of the deck is left to be exposed, a vapor retarder and rigid insulation can be applied above the deck and below the roofing. So just another location for it. Much less common. So let's talk a little bit about shingles. Okay, we talked about shingle siding earlier. Shingle roofing is virtually the same thing, right? But the term shingle can describe wood, but it can also describe asphalt, right? It can describe slate. It can describe clay tiles. It can describe concrete tiles, right? So we've got a lot that can be categorized as shingles. They're all applied in small units, right, that are repeating and that the joints are all staggered. Okay, so wood shingles are thin tapered slabs of wood. They're sawn from the trunk of the tree with grain running roughly parallel to the face of the shingle. Shakes, on the other hand, you've probably heard of shingles versus shakes. Shakes is the same concept, except instead of being cut, right, they're actually split. So they tend to be thicker, and they tend to have a rougher texture to them, okay, which might be an advantage, might not be an advantage. The problem with wood roofing is that it's, really, it is exposed to rot, so you either have to do it out of cedar or you have to do it out of redwood, right? You're not going to pressure treat shingles. And the other thing is that what can happen is if you are in a fire danger area, right, it's really easy to catch a roof on fire, so it's not considered a particularly fire-safe building material. So we're going to tend to use things like asphalt or sheet metal to resist fire. Okay? They typically will last 15 to 25 years. I've seen them last 40. It just depends on the quality of the shingles when they were put up in the first place. Asphalt or I call them composite shingles, composition shingles, are die cut from sheets of asphalt, right? So much like what we're looking at here, they take a sheet of this, right, and they cut it, right, and they glue a couple of the sheets together such that it gives us a little bit of a texture that looks kind of like a shingle. Okay? How many people have this kind of roof at home? I do. Okay? They're typically going to come 12 feet, right, by 12 inches by 36 inches. Okay? Those sheets are designed such that it's very difficult to find wherever the seam is. Okay? So it's going to span usually up under at least one layer here. So you have one exposed and one goes under. This one then slips over the top of the one previous. They're generally very inexpensive. They're very quick to install. They're relatively fire resistant, and the book says 15 to 25 years. You can buy this kind of roofing that is rated for 45 to 60 years. If you buy a 45-year roof or a 60-year roof from Home Depot, it's going to last about half the time it says it's going to last. Just the way those kinds of roofing works. So don't actually think you're going to get 30 years out of a 30-year roof. You maybe get 10 or 15. Just the way it is. Okay? So here's our example of this. We're rolling out our felt, right? Again, always from bottom to top of our sloping roof, right? After we've rolled out felt, right? Then we're going to lay down, right, our starter course, which is just a single row here. Then we're going to lay on top of that, right, one row. And again, we're going to stagger our joints back, again, starting from the eave, working our way to the ridge, right? So they're always overlapping. Okay? The problem is if you have a leak and you've got to tear it off, you've got to start from the top and tear it down, right? Or find a way to slip underneath a particular layer. It can be very challenging. Okay, so here it is getting all the way to the top, right? And usually there's some kind of a ridge unit that's designed to span the ridge, right, and fold together and seal off the ridge. Sometimes it has a vent built into it. Make sense? Eave to ridge, always. Okay, these are looking at a valley. Okay, there's a couple different ways of doing it. In this particular instance, we have a set of sheet metal that runs down the valley, and we've cut our shingles back, right, so that water that flows into that valley will flow down the sheet metal. Okay, I like this method personally because I know it's nice and safe, and I'm not going to get problems with it. The other type of valley is called a woven valley, where one shingle will run one way long, the other one will run the opposite way, and they'll weave over the top of each other. I had a building that was built in, the roof was probably put on in '97. This was a couple years ago. I had one of these valleys fail, right, and I got water through. It started rotting, went through into the apartment, all that kind of stuff. Had to tear off that whole section of roof, which is why I don't really like those ideas, that type of woven valley. I didn't put the roof on in the first place. I just had to fix it, okay? But I like this method a little bit better. They have a very different look, though. The last method is where you lap one way and then this way comes across and it's cut. That I really don't like. Okay? Just have to be honest. Anybody a roofing contractor? Am I insulting anybody? Good. Good. Phew. All right. So what about slate shingles? Okay, you've probably seen this. If you put it on your house, good for you. Not something I could ever afford to put on my house. It's stone, so it's a very resistant material to fire. It's a very resistant material to weather, so that's great. They can crack. They come to the site split. They can vary in thickness a little bit. Usually they have holes drilled through that allow you to attach nails. They're very fire resistant. They're very, very expensive when you first put them on, but they will last for a very, very long time. The book says they'll last 60 to 80 years. I'd say you can get much more out of them. Okay? Again, it's stone. It's a natural material. Nothing's really going to happen to it as long as you don't walk on it and crack the tiles. Right? That would be the big disadvantage. Okay? You can also have clay tiles. How many people have something like this with clay tiles on the roof? Really? Wow, in California.
Very common.
It's very common around here. Okay? So this is, again, a very fire-resistant material. It's a clay tile. They tend to follow this shape. I'll show you the example for drainage purposes in terms of how you put it together. They're very heavy, though, and that's something to be aware of. You have to engineer your building to withstand the loads that are there. They're resistant to fire. They are also expensive in the beginning, not as expensive as slate, certainly, but they're still more expensive than an asphalt shingle roof, for example. But they're going to last 30 to 75 years, which is a big benefit. So you're not going to be re-roofing as much. So this is the drawing that kind of explains how these work. We have the tiles that are relatively uniform, right, no matter which way we flip them, but we're going to use them in alternating methods. So in one sense, they're going to be horseshoes. In the other sense, they're going to go over the top. Okay? And when that happens, right, we have these various pieces, and then this stack slides over the top of the previous stack, so we end up with a really nice waterproof barrier that allows the water to shed off the roof. Okay? And the other thing is, in heavy wind areas, they're heavy, right? So they're not going to blow and flap off, which is another big advantage. These are concrete roof tiles, which is also common, especially in fire areas. Same concept, it's just a concrete tile that's been cast in a particular shape. That's used, right, and they look more like slate, really. They're usually a little bit thicker. They have nail holes at the back. Some of them have grooves that interlock with the one next to them, which helps them stay close together. Again, heavy, high first cost, but they're going to last for a really long time, which is a big benefit. One side note, I had a job where they had these kinds of tiles. The house was built in the 80s, and they wanted to do a remodel and kind of an addition to the house. And when they did it, they needed to extend the roof tiles. The problem was they didn't make those roof tiles anymore, right? So sometimes if you go into this concrete tile realm, you can end up not being able to match a roof tile if you want to add later on. So it just depends on if the company that made the tiles in the first place went out of business. So we found matching tiles. They were just missing the scallop on the edge, so we ended up taking off half the roof and moving that half to the front half and doing on the addition, the part that you would only see from the backyard has the new tiles without the scalloped edge on it. So they were close in the same color range, not quite the same, but you couldn't really tell. So it worked out okay. So the thing about steep roofs is depending on which material you pick, they have a minimum slope. So if you're doing asphalt shingles, for example, the minimum slope is 4 and 12, right? So 4 inches of rise for 12 inches of run. You can't do a 3 and 12 roof with asphalt shingles, or the water can actually work its way back up into your roof, which fails. Okay, so you need to pay attention to whatever the manufacturer specifications are for that particular roof. So the last type of roof we'll talk about is architectural sheet metal roofing. Okay, and so this is if you have sheet goods, right, and you're putting those sheets together to form basically a metal roof, which can be a really big advantage depending on how you do it. The seams are designed to maintain watertight, but they also allow for expansion and contraction, because remember, steel, right, or aluminum expands and contracts at a different rate than the wood in your house, so you have to plan for that. Okay. The other thing is that seams do create a very strong visual pattern on the roof, something to be aware of. Okay. Generally, they have a high first cost, and the book refers to they last for, quote, many decades. Yeah. Could you be more vague? You know, basically, a roof like this is going to last as long as the finish lasts that protects it from the weather, right? Or as long as you don't ruin it somehow by walking on it or putting a nail through it. Okay? So it can be a really long-lasting, efficient roof. Now, there's a variety of materials that can be made. Originally, a lot of this was made by lead. Okay? Problem is lead is really toxic, so we've gone away from using lead as our roofing material. Copper is wonderful. It gives a nice green patina over time. Great if you're in a kind of an ocean environment because it just has a nice quality to it. The problem is it's really, really expensive, right? So you might not go that method. You can do stainless steel or titanium if you have the budget for it. Not something I have the budget for. You can also do zinc. It's usually zinc-coated steel, right, which is basically a galvanized steel. It'll rust over time. And you can also do aluminum that's been basically painted with a very special coating, which is kind of the most common method today for this kind of a roof. So you can basically pick it whatever color you want and then make that type of roofing. So we've got what's called a flat seam metal roof. And so in these particular instances, right, we're using this, right, we have one piece here, we take the second piece and we slide it over the top of the first piece, right, and then we fold the whole piece over one more time, right? So through that process, right, which takes a little bit of time, we end up creating a watertight seal, okay? Usually it's done by machine, you're not out there with hands doing it. We also have what's called a standing seam metal roof, okay, same concept, right, where we put our two pieces together, we have our pieces coming out here, we fold it over, and then fold it over on itself again, right, and through that process of folding the seam, we end up creating a nice watertight barrier. Now the nice thing is, in this book example, right, we have sheets that are overlapping. If you're doing this kind of a metal roof, I'll get to you in just a second. If you're doing this kind of a metal roof and you have a roofing contractor that does this, sometimes they'll do it seamless, right, where they come out to the site with a big roll of whatever the roofing is, and they'll fold it on site in however long of a piece you need, right, and then install that piece on the roof. So there's no seams. So once you seam sideways vertically, right, you can have as long of a run of a roof as you want, and there's not a single seam in it, which is really nice. You had a question?
So is that the vertical seam?
Those are the vertical seams, right? So if you're looking at the building, they're running like this along the building. Exactly. And it can be a really nice look. This is a batten seam metal roof, which is the same concept as a standing seam. We just have a wooden batten, right? And then we're putting a cap that gets folded over on itself, right? That creates the same kind of a seam, but it's a flat with then a little raised hump and then flat with a little